And I know we're here till the very, very end. Today is our last day.
Last
Okay.
day.
All right, Ms. Rondo, you should be seeing my screen now.
Yes, we are.
Okay. All right, I'm going to go right back to the right examples. Okay, here we go. All right, so we're going to hit more factoring today. And so we're going to review some of our factoring and add the trig layer onto it. And this is just good for you to see because there are, it's just a lot of, it's just good to see math manipulated in different ways. We may or may not actually see something like this in calculus, but it kind of gets your brain thinking, okay? So I am always going to try to replace as much as I can. Actually, I want to replace first. I'm going to use a trig identity and then do some factoring because look at this and this don't match, okay? I want them to match. So I know that I've got a trig identity because that's a squared. I know I've got a Pythagorean identity that says sine squared plus cosine squared equals 1. And I could solve it for it's not that way. I could solve it for sine squared. I could move this to the other side. So sine squared equals 1 minus cosine squared. So I'm going to take that and substitute it in here. So that gives me 2 times 1 minus cosine squared x plus 3 cosine x minus 3 equals 0. I'm going to distribute this in. So I've got 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. And it looks like I have some like terms. So I've got this 2 and the 3 I'm going to put together. So negative 2 cosine squared x plus 3 cosine x minus 1 equals 0. I think we're doing okay so far. I'm going to fix that a little bit. All right. When I see something like this, when I have a negative leading coefficient like that, negative leading coefficients tend to not be so nice. And I'm going to be really, really sloppy about this. But I'm going to switch. I'm going to basically multiply everything by -1, okay, which I'd have a -0, which is just still 0. But so I basically swapped all my signs so that my coefficient, my leading coefficient's positive. So now I'm going to rethink about this. Now that I have these guys matching, I'm going to think about it like 2x squared minus 3x plus 1 equals 0. And how would I solve that? Well, I've got to do good old magic x. So two numbers that multiply to 2 and add to -3. And I think that that might be -2 and -1. And then remember, when we have a leading coefficient, we need to get out the box. All right. And then 2x squared and 1, -2x and -1 from the magic x. Two numbers that multiply, to 2 are 2 and 1, but 2 does not multiply into the 1, it multiplies into the 2 here. And then 2x divides -2, -1 times, and 1x divides -1, -1 times, and then I check, -1 times -1 is 1. So I'm going to rewrite that over here, but I'm going to replace the x's with cosines, whatever's in the middle here. So cosine x minus 1 times 2 cosine x minus 1 equals 0. We're going to now apply our zero product property. So cosine x minus 1 equals 0, and 2 cosine x minus 1 equals 0. And I'm going to add the 1 to the other side. So cosine x equals 1. And then I'm going to add this one. So 2 cosine x equals 1, and cosine x equals 1/2. So now I need to get the x that's trapped inside the cosines out. So I'm going to take the cosine inverse of both sides. And I'm not skipping this step because this is where we lost it last year. So I'm going to make sure we've got it this year. So I need to find cosine inverse of 1. And then cosine inverse of cosine x equals cosine inverse of 1/2. Those cancel, so x equals cosine inverse of 1/2. We are luckily on 0 to 2. Sorry, 0 to 2 pi. So I get to use only that first revolution of the unit circle. And I'm going to scroll up. I'm sure I've got a unit circle there. So I'm looking for where my cosine is the x value. So I'm looking for x equal to 1 and x equal to 1/2, all the places that that happens. So I'm going to find a unit circle here. Here we go. Maybe I can copy and paste that. Hang on. I think I can do that so we can write on it. Control C. Oh, that's interesting. All right. I squished it. Hopefully I copied it.
Oh, it worked though.
That's better. See? Editing on the fly. Actually, I'm going to move it over just a bit because I'm going to have to, I'll run into it here with that other problem. Okay. Easy peasy. Okay, so I'm looking for where my x value is 1. So I'm going to go all the way around my circle. I know my x value is 1 there, and really I should have a 0 radians there, so I know that at x equals 0 radians that happens. I'm looking for more 1s in the x spot, and I don't have any more positive 1s, so that's the only thing I get off of that half of it. I'm going to look for where x equals positive 1/2. I see it here, which means I get pi over 3. I'm looking for positive 1/2. Oh, I see it here, and I get 5 pi over 3. Those are my those are my 3 answers that are possibilities to solutions for that equation. All right, 18 is actually fairly similar. So I'm going to do 18, but it's going to just have a slightly different trig identity, but a very, very similar one. I'm seeing, again, these guys don't match. I'd like them to match. I know I can use something Pythagorean on that likely, so I'm going to try to find a Pythagorean identity. And I believe 1 plus tangent squared equals secant squared. Am I right, Ms. Rondeau?
Yes.
Okay, and that's one that we don't even have to manipulate, so I can just take this guy and plug him in over here. So 3 times 1 plus tangent squared x minus 2 tangent x minus 4 equals 0. And then I'm going to distribute this in. So 3 plus 3 tangent squared x minus 2 tangent x minus 4 equals 0. And I'm going to combine this and this together. So 3 tangent squared x minus 2 tangent x minus 1 equals 0. I think that's almost, no, it's different. It's a different magic x. Bummer. All right, we're going to do magic x again. So again, I have these guys here. I'm going to just pretend like they're x's for a minute. So I really am doing 3x squared minus 2x minus 1 equals 0. So magic x would give me 2 numbers that multiply to -3 and add to -2. So I'm thinking -3 and 1. And because I have that leading coefficient, I'm going to get out that box again. The good news is in calculus, we don't tend to see ones with leading coefficients very often. It's almost just a leading coefficient of 1. Kind of nice. All right. 2 numbers that multiply to 3 would be 3 and 1. My 3 would have to go on the side. And 3x divides -3x, -1 times. 1x divides -x, -1 times. Ooh, what did I do? Something went wrong somewhere. Oh, I put a negative here. Oh, no, it's supposed to be negative there. What did I do wrong?
Negative, positive, hold on. Your negative x should be a positive x.
Ah, yes, that's where my mistake is. But see, you guys, I was able to catch it because I had that in that I knew that they weren't multiplying outright. So it was actually easy for me to catch. I knew I was doing it wrong. All right, I didn't transfer this over correctly. That's what happened. So I know that, what did I have there? So I know 1x divided by 1x is 1, and then 1 times -1 is -1. So now I know I'm confident I have it correct, especially before I go put the trig back into it. So I'm going to substitute my trig in for my x's. So 3 tangent of x plus 1 times tangent of x minus 1 equals 0. And we're going to get out the good old zero product property. So 3 tangent of x plus 1 equals 0, and tangent of x minus 1 equals 0. 3 tangent of x, I'm going to subtract the 1, and then divide by 3. And then over here, I am going to feel like I'm doing something wrong. Oh my goodness.
Did I miss something?
I don't know. No.
No.
I might have my answer wrong in my original copy. That's what's probably wrong. I'm good, I think, because this and this are -4, right? Or -1, right?
-1, uh-huh. Yeah.
Oh, I see what happened. Okay, never mind. I see what I did wrong. I see where there was a typo in the problem, possibly. I'm not sure we're going to get anywhere with what we're doing. Equals 1. All right, we can get somewhere with this side.
So the other one's extraneous. It's okay.
Yes, yes, that's what it's going to be. Squared on the tangent, which is what it was supposed to be, it would have come out a little different. But that's okay. We're going to work with it. So, all right. So what Miss Rondeau just alluded to is that, remember, when we're working with tangent, it's the sine over the cosine. And remember, our unit circle, we know everything divides by 2. So we know we would have had to do something like that. But what's missing on this is a square root of 3. So that ends up being an extraneous answer for us. So we're not going to get anything from that side. What was that, Miss Rondeau?
I said, yeah, it didn't work. So another thing to kind of help out with those extraneous solutions, we've seen them a few times with trig. When we are talking unit circle, we know the radius for the unit circle is 1, which means all of those ordered pairs that are around the unit circle, the values have to be less than 1. So if you're looking at tangent x equals -1/3, your sine is -1, your cosine is 3. That doesn't make sense. You can't have a cosine of 3 that's less than 1.
Yeah.
Anyways.
Yep. I totally agree.
Doesn't make sense.
Right. So I'm going to go ahead, and I do know I can do something with this 1 here, though. So I'm going to do my tangent inverse on this branch here. So tangent of x equals tangent inverse of 1. I know these guys would cancel, so I'm just going to get x equals the tangent inverse of 1. And remember, it's really like saying 1/1. Or really what I'm looking for is where the sine and the cosine are exactly equal. And remember, it could be positive equal or negative and negative equal. So we've been doing a lot of unit circle, and I know that they're exactly equal at pi/4, and they're exactly equal at 5 pi/4. So those would be the two solutions we would get on this one. So pi/4 and 5 pi/4. All right. And I really, Miss Rondo, I think I am going to just skip 20. I'm just going to do 19.
Okay.
They are really identical.
Yes, they are.
Same factoring and everything.
Yep.
All right. So this one is a little bit weirder. Okay. There is nothing there that we can replace with a trig identity, but we still know that we need to get it down to one trig function. It either needs to be sine or it needs to be cosine. So remember, we have rules in math that whatever I do to the left side of the equation, I have to do to the right side of the equation. We've seen that when we have something squared, we can use a Pythagorean identity to replace stuff. So that's where I'm going to go with this. I'm going to say, no red. There we go. I'm going to square both sides. Okay. So what that means is that here on the left side, I would be doing cosine x plus 1 times cosine x plus 1 equals sine squared x. And I'm going to go ahead and FOIL that out. Okay. So cosine times cosine is cosine squared x. Cosine times 1 would just be cosine x. And I'd have another cosine times 1, which would be another cosine x, which really means I have 2 cosine x. And then I have 1 times 1, which is just 1. Sorry, I'm looking at my notes too at the same time.
You're good. I think it's really, sorry, it's not super important, but really interesting as you're doing it, thinking that that's exactly how I did it. So there's a million ways to do these, and it's just funny that we do it the same way. That's good.
Yes. All right. And then now I've noticed I have a lot of cosines on the left side, but I still have a sine on the right side. So I do know that I have that identity. And I think we did it earlier. I'm going to steal it. We did it right here. We know that sine squared plus cosine squared equals 1, or when I move my cosine, I can substitute in 1 minus cosine squared. So I'm going to do that. 1 minus cosine squared x. cosine squared x plus 2 cosine x plus 1. All right. So I am going to choose, it is looking, there's a squared, which means it's somewhat quadratic. So I'm going to move both of these to the other side. So when I move my cosine squared, I get cosine squared x plus cosine squared x is 2 cosine squared x. This guy didn't have any friends, so I'm just going to, so sad, I'm just going to write him down. And then this one I have to subtract to the other side. So 1 minus 1 is 0, so I'm not even going to write anything for him. Then we get that it is equal to 0. I'm going to have to factor, but it's not a magic X. I know we're all bummed out about that.
I'm so sad.
I know, that's rough. But if you look at this one and then you look at this one, you'll notice they both have a cosine in them. So we're going to do some greatest common factor factoring. So I'm going to pull out a cosine. In fact, I'm going to pull out a 2 cosine because if I can get rid of that coefficient, even better.
That was my suggestion. You got it.
Yes. When I pull it out of there, I am left with just a cosine x. When I pull it out of here, I would only be left. Remember, there's always an invisible 1 in front, which equals 0. And now we're back to zero product property. So 2
Woohoo!
cosine, I know, woohoo, equals 0, and cosine x plus 1 equals 0.
We're getting good at that zero product property.
I know, we really should be. We should be able to do that baby in our heads. So I'm going to divide by 2. So 0 divided by 2 is 0. And I'm going to subtract the 1. So cosine of x equals -1. And you'll notice, you guys, it's not that these problems are hard, but they're long. They're a little tedious. Okay. So you just kind of got to stick with it because you got the trig layer on top of the algebra layer. And then I'm going to do the cosine inverse of both sides. Oops, I missed the cosine inverse on the other side.
Mrs. Ballard breaking the rules.
I'm not, yeah, I don't want to break the rules.
No. The math gods will come and get you.
Yes. Good thing they're trapped on the posters in my room.
Yes, good thing.
Yes. All right. The cosines cancel. So I've got x equals cosine inverse of 0. And again, the cosines cancel. X equals cosine inverse of -1. That's just a page number there. Sorry. All right. We're going to look, cosine is the x value. So I need to look at my unit circle where the x value is equal to 0 and find the radian measure. So I'm going to sneak back up here to my circle. I'm looking for an x value of 0. Here's an x value of 0. So pi over 2. I'm still looking. I'm still looking. I'm still looking. Here's another x value of 0, 3 pi over 2. So x equals pi over 2 and 3 pi over 2. And then we're also looking for where an x value equals -1. So I'm looking for -1 and all of, oh, here's one here, pi. And I don't see any others, just pi. X equals pi. All right, Andy, are you ready for the jokes?
Sure.
Do we have any questions or concerns in the chat, Ms. Rondeau?
No, we're doing good.
Okay, so let me stop sharing my screen. And Andy has 2 good ones today. He practiced
All right.
them. So hopefully he remembers them. All right, Andy, you ready?
Yes.
Okay, tell us the jokes.
Knock knock.
Who's there?
Poly.
Polly who?
Polynomial? Why the 3rd degree?
Okay.
We had to practice how to say the word polynomial a few times, but he got it.
You got it. Nailed it.
He did. He nailed it. All right, Andy, what's the second joke?
What's 2n plus 2n?
I don't know. What's 2n plus 2n?
I don't know, but it's foreign to me.
Good job. Good enough. All right, Ms. Rondeau, we are up for, I'm looking forward to some multiple angle identities.
They are pretty fun.
They are.
Okay, I'm getting my screen up here. Hopefully you guys are seeing apparently the unit circle. What number am I starting on? 23. Okay.
Yes, 23.
All right, so we are looking at multiple angle equations. So as much as Miss Ballard just said multiple angle, the reason for that is if we look at this trig function in this equation, it says cosine of 3t. So the 3t represents our angle. What we would have said was x or theta. that is an expression that's representing the angle. So I'm going to leave parentheses around there just to kind of help us. That's the angle. We're going to solve this just like we did before, get the cosine by itself. So I'm going to start by adding 1 to both sides. And I get 2 cosine of 3t equals 1. And then divide by 2. And cosine 3t equals 1/2. All right, so when I do this problem, I'm going to still not worry about the fact that it says 3t. I'm just going to think of this whole thing as my variable, my angle I'm trying to figure out. So I'm going to keep going. I need to get rid of my cosine, so I'm going to cosine inverse. And of course, I do it to both sides. And so the cosines cancel. I have 3t equals cosine inverse of 1/2. All right, so the way that this works is I'm going to deal with the 3t in a minute. For the moment, I'm going to look at my unit circle and find my x values that are 1/2 on the unit circle. I'm going to figure out which angles have an x value of 1/2. So let's look at the unit circle. I'm looking for x values of 1/2. In my unit circle, it looks like right here, there's an x value that's 1/2. So that would be an angle of pi over 3. I'm going to keep looking. Here's another one, x value of 1/2. And that one would be at the angle that's kind of hard to see down here. It's 5 pi over 3. And so I think that's it. We're good with those two angles. So I'm going to come back and I'm going to actually build 2 equations. So my 2 values that worked for this were pi over 3, I believe, and 5 pi over 3. So I'm going to build 2 separate equations. One that says 3t, the angle, is pi over 3. That was one of the options. Or the other one is 3t equals 5 pi over 3. So our angle that's represented by 3t has to be either pi over 3 or 5 pi over 3. So then we're going to solve to figure out what t actually is. So to solve this one, I want t by itself. So I'm going to divide by 3, which is the same, even though I'm writing divide by 3. Remember, dividing is the same as multiplying by the reciprocal. So instead of divide by 3, I rewrote it as multiply by 1/3. And I did not give myself enough room. I'm just going to erase this and put it back in a second. Okay, so then I end up with one of my possible answers for t is pi over 9. And then the other one is just solve the other equation in the same way. So this one, since I already saw that dividing by 3 was multiplying by 1/3, those are the same. I'm just going to shortcut this a little bit and I'm going to multiply both sides by 1/3. So here you can see the 3's cancel. I have t. On this side, I have 5 pi over 9. So t can be pi over 9 or 5 pi over 9. Awesome. And we are within 1 unit circle, just to clarify, make sure we double check that. Yes, we only care about 1 time around the circle. All right, next one. Same basic idea. We're going to, again, I'm going to remind us that the pi over 2 is the angle. So we're going to get to the x eventually, but we're going to focus on this concept as finding the angle. So I'm going to just do my regular algebraic solving, subtract 3 from both sides. And then divide by 3. And I get -1. So then I need to get rid of my tangent. So I'm going to inverse tangent. Sorry, it takes me a while to write all that, as I'm sure it takes you guys a while to write it too. There we go. And so my inverse tangent gets rid of my tangent. I have x over 2 equals tangent inverse of -1. So for this one, since it's tangent, remember tangent is the same as y over x. And if I look at this -1 and I create a fraction really quickly, I'm looking for that same. Same. So it's 1 and 1. I do need a negative for my my fraction overall. But when I go look at the unit circle, I'm looking for the x value and the y value to be the same, because they're the same here. So remember, I think I did one where I was like 1,000 over 1,000. Happy face over happy face. It doesn't matter. They're going to be the same. So definitely want the values to be the same, and then one of them to be negative. Not both on this one. So same number, but only one negative value. So let's look at the unit circle for where our x and y's are the same. So I see right here the same, but they're both positive, and I need my answer overall to be negative, so that one's not going to work. So I keep looking, and I see same, and I do have that one negative. So this is what I'm looking for. Same, and then one of them's negative. There's my angle, 3 pi over 4. I'm going to look for another place where we have that. In quadrant 3, I see same, but they both have a negative, which means when I stack them into my fraction, I'm going to do negative divided by negative. That's not going to work out to what I'm looking for. So that one doesn't work. And then over here, same, and I have that one negative. That's what I'm looking for. There's 7 pi over 4. So I have 3 pi over 4 and 7 pi over 4. All right, so then once again, I'm going to build this into two equations. So I have x over 2 can equal 3 pi over 4, or x over 2 is going to equal 7 pi over 4. Okay, and then I'm solving now to find x. So my angle, my x over 2 represented my angle is one of those two, 3 pi over 4 or 7 pi over 4. Then I just solve for x. So I'm going to multiply by 2 on this one, both sides. So that would be 2 over 1. Those cancel. I get, here you could just multiply across and get 6 pi over 4. Or if you cross canceled, that's fine too. And we reduce that either way. We're going to end up with 3 pi over 2. And the same basic process here, multiply both sides by 2. I get x equals 14 pi over 4, which reduces to 7 pi over 2. Awesome. So we have those. Any questions? How are we doing, Mrs. Ballard?
Think we're doing good.
Awesome. Feel free to jump in and add anything if I miss it too.
I will.
Awesome. All right, so here we have secant. This one is set up as secant of 4x. So I'm going to remind us that 4x is the angle. This one, it's already basically solved. We just have to get rid of the secant. So I'm going to do secant inverse of secant of 4x equals my secant inverse, of 2. And so the secants go away, and we have 4x equals the secant inverse of 2. All right, so I'm going to remind us that secant is the same as cosine, just the reciprocal. So you could work with this as, what am I looking for? Cosine. The cosine inverse version would be cosine 1/2, because 1/2 is the reciprocal of 2. Or you could stick with secant and just make this 2 over 1. It's a little bit easier to do it as cosine because it matches up with the unit circle nicely, because cosine is going to be your x value versus secant is going to be 1 over x. So you have to think about all of your numbers in a different way if you look at it as secant. So I would say use cosine and look for the x value of 1/2. And then we're going to have to go back and figure out what angles those are and so forth. So let's look at our unit circle. We're looking for an x value of 1/2. So x value of 1/2, I see one here at pi over 3. X value of 1/2, I see it down here at 5 pi over 3. Awesome. Well, let's go back. So my two options were pi over 3 and 5 pi over 3. So I'm going to one more time build that equation, one for each possible angle. So I'm going to say my angle, which is 4x, is either pi over 3 or my angle is 5 pi over 3. All right, so then I'm going to solve by dividing by 4. But since I have that fraction, I'm actually going to remember my work from before. Instead of divide, I'm going to multiply by the reciprocal. Multiply by 1/4 on both sides. And if you put a 1 under that, you can see there's your 4's canceling out. I have pi over 12. And then same thing here, multiply by the reciprocal. 4's cancel, and we get 5 pi over 12.
It looks
Fantastic.
good, Mr. Rondo.
What's that?
It looks good.
Awesome. Everything is awesome. Oh, no, never mind. Okay.
Oh, I can do that.
Maybe at the end.
Okay.
Okay. All right. So number 26, doing that same, again, working in the same world of we have a funky written angle. I'm just going to put parentheses around it and say, okay, that represents my angle. And then I need to solve to get to the angle. So I got to get rid of tangent. So I'm in a tangent inverse. And if I do it to one side, I got to do it to the other side. All right, so the tangents go away. I have x over 3 equals my tangent inverse of 1. So for this one, remember tangent is going to be y over x, sine over cosine. So we're looking at the two values here. If I make this a fraction, that means I'm looking for 1 over 1 or same. And this Mrs. Ballard mentioned earlier that this could have come from a negative for both. So literally the same in the top and the bottom. In the numerator, -1, and denominator, -1 would still end up giving me that 1 that I had over here. So, and again, we're looking for same. So it doesn't literally have to be a 1. As long as the two values are the same, both positive or both negative, we're going to be okay. So let's look at our unit circle, looking for the x value and the y value to match. I see that here at pi over 4. And looks like down here in quadrant 3, negative root 2 over 2, negative root 2 over 2. Those are completely matching. So those are going to work as well. All right, so we have pi over 4 and 5 pi over 4. So pi over 4 and 5 pi over 4. All right, so I'm going to write two separate equations that says, okay, my angle was x over 3, and that could be pi over 4, or my angle of x over 3 could be 5 pi over 4. And then we're going to solve. So I'm going to multiply by 3, both sides, and I get x equals 3 pi over 4. If it helps you out, go ahead and put a 1 under these. Might be a little bit easier to see your fractions. Same thing over here, multiply by 3, and put a 1 under these to help me out. I get x equals 15 pi over 4. And that is it.
It looks
Questions?
good. I don't see any.
Let me get rid of sharing my screen for you guys. Sorry. There, should be back now.
Yep.
Awesome.
All right, guys. Today is our last day. We're giving you Friday off. You get the last day of school off.
Yay!
That's awesome. Yay. So remember, we're going to put one more assignment out there. We need everything by 5 o'clock tomorrow. There has been an error message in PowerSchool that says it's going possibly offline at 7 p.m. Eastern, which is 4 o'clock our time tomorrow. So if you need to turn it into PowerSchool, do it before 4. Don't wait till the last minute. Okay. Other than that, it's been great to have you guys. We look forward to seeing you in the fall.
Yes, awesome. Thank you guys so much for coming and working hard on all this stuff. It really will help out next year in calculus. We have another joke?
Do you have another joke? No. He
That's
didn't
okay.
memorize another one. So we'll have more jokes from Andy next year. Something to look forward to.
That's my summer project.
He's got a summer project.
180 of them.
All right,
nice.
guys. We will see you next fall. Okay. Bye, everybody. Yes, you will get a joke every day. We're going to do 180 jokes over the summer.
It's important, you know. This is the reason to take calculus, to hear joke of the day from Andy.
Joke of the day from Andy. It's the new thing.
You know that's not nice, right?
What's not nice?
Come on, I have to do 180 jokes.
Yeah, that's fine. Casey says she can't wait. She's looking forward to it.
Yeah.
Yep. Apparently, the jokes of the day are a hit. All right, bye, guys. See you later.
Been fun. Have a good summer.
From the moon. Meeting. Remove her. I'm moving from the meeting. Remove her.
All right, I got rid of the last one.
Okay. Yeah, no problem. I was playing
So
with that. Like,
yesterday I was going to tell you one of the sentences supposedly that was in the hang on, I got to stop recording.
yes.